Hi and welcome to this Leaving Cert Higher Level Calculus video. Today we're going to be focusing on stationary points, including the minimum and maximum turning points, minimum and maximum points, saddle point, and the point of inflection. So let's start with quadratics. When we see these two quadratics, we have a positive and a negative quadratic. It's important that you understand not only how to identify these from the graph, but also how to identify these from a given function. So in order to figure out if a graph is positive or negative, we can use the simple positive people smile, negative people frown. So the graph on the left, smiley face, is positive. The graph on the right, frowny face, it is negative. When we look at the function, so ax squared plus bx plus c, we look at what's called the leading coefficient. So this is the coefficient in front of the x squared when we're talking about quadratic functions. If that a is greater than 0, that means positive, then the whole thing is positive. If the a is less than 0, i.e. negative, then the whole thing is negative. We're looking today at turning points. It's important to note that for quadratic functions, you either have a minimum turning point or a maximum turning point. We will never have both. A positive quadratic will always have a minimum turning point, and a negative quadratic will always have a maximum turning point. This might sound basic, and you might be saying, yeah, I understand this. But if you have a really good grasp of this, it will really help you as we get on to the second derivative test. If we look at a cubic function then, most cubic functions, and I say most because you don't have to have two, but most cubic functions are going to have a minimum and a maximum point. And we need to be able to work out not only the 2 points, but which one is which. So in order to find the turning points of any function, you find the slope of the tangent, which is dy dx. You then, at that turning point, you know the slope is 0, so you will let dy dx equal 0. So you let the slope equal 0. You solve for your x values, and then you plug those x values back into your original function to find the second coordinate, the y piece. Going back to our cubic here, hopefully you can see that at both of these points, if I draw a tangent, it's flat. That means that it has no slope, or the slope is 0. In order to get the slope at any given point, or the slope of a tangent, we differentiate, so dy dx. So starting with the cubic function y, we differentiate dy dx to find the slope of the tangent, and we know at these 2 points, the slope of that tangent equals 0. That will allow us to solve for x, and once we have our x values, we plug those back into our original function to find the corresponding y values. Do take care in these questions if you're asked for a value of y, a value of x, or a coordinate which includes both of them. Let's look at an example. Find the turning point of the following function and identify if it is a minimum or maximum turning point. Okay, so the first thing we're going to do is to find slope. So that is first derivative, dy dx. We're going to differentiate it. We get the 3 disappears because it's a constant, minus 2 minus 10x. I think it's a really good habit to get into to always label dy dx as slope. Just to remember, especially think of an exam situation where you're very stressed, this kind of thing can easily slip your mind. You know this, but just as a fail-safe, write it in beside it. We're trying to find the minimum or maximum point. We know that this happens when the slope is 0. So we let the slope, minus 2 minus 10x, equals 0. So we get minus 10x equals 2. So x is equal to minus, it simplifies to 1/5. So now that I have my x value, I want to get my y value. We always sub back into the original function to find y. So it's 3 minus 2 times minus 1/5 minus 5 times minus 1/5 squared. You can put that straight into your calculator. It gives us 16/5. If you really feel like it, you can turn those to decimals. I'm not a huge fan of decimals. I much prefer fractions, but no issue here because there'll be no rounding involved. Okay, so we have our point. That was the first part of this question. So find the turning point. And then the second part was identify if it's minimum or maximum. Now I'm going to show you some ways that we can do this, but I will always err on the side of let's do as little work as possible. So we have here a quadratic. At higher level, you should be able to identify that this thing here is a negative quadratic. If you can't, you need to learn that. The reason it's negative is because it has a negative leading coefficient. Now, don't be put off. It's not always the first thing. It's what is in front of the x squared. Often they rearrange a quadratic when it's negative, so the negative isn't out in front. It's very easy to lose a negative if that minus is written at the very start. So often we see this rearranged to capture that minus. Don't get tricked. So if I have a negative quadratic, it means the turning point I have is actually a maximum turning point. You didn't have to draw it out. However, if you want to see it visually, you can. That's a very quick way to do it. Like I said, I will show you other ways to check whether it is minimum or maximum. So now let's look at a second example where we have a cubic function. It says find the coordinates of the local maximum point and the local minimum point. Okay, so we need both. So just like we did before, the first thing I'm going to do is get slope. That is the derivative. So remember, dy dx, so differentiating y with respect to x, is the same as f dash of x. I would always say answer the way that they gave us. They gave us f of x, so we use f dash of x. This gives us 6x squared plus 10x minus 4. Remember that this represents the slope. To get the turning point, the slope is 0. So we let this quadratic that we've just found equal 0. And now we solve. I'm going to simplify it by dividing it by 2. You don't have to, but it just makes your numbers a little bit smaller and a little bit easier to work with. I would suggest using guide number here. It's up to you. I'm going to use a bit of trial and error just to speed this up. So if you're kind of looking going, I don't know what you're doing, it's fine. You would work this guide number or minus b, but look, minus b is slightly excessive for this. So if we worked through with the guide number, we should get 3x minus 1, x plus 2 equals 0. Solving this gives us x equals a third and x equals minus 2. Now, I know I've changed what's on top, but we're in the same example. So now I have x, I need to find my y, and I'm going to show you another way we can figure out if it's positive or negative. Quadratics are very straightforward, but here we're going to have 2 points and we need to figure out which one is which. So I'm going to sub this back into the original. So I'm going to do f of minus 2. So that's 2 times minus 2 cubed plus 5 times minus 2 squared minus 4 times minus 2 minus 3, and we work that out. And we get 9, so my point is minus 2, 9. Often students sub it back into the derivative rather than the original function, so if you ever get a 0 there, just double check. That's usually an indication you put it into the wrong one. Now I'm doing f of a third, so it's 2 times a third cubed plus 5 times a third squared minus 4 times a third minus 3, and into the calculator. And that gives us a not so nice minus 100 over 27. So that point is a third minus 127. Now, so this is the second way to check if it's a minimum or maximum point. It will only work really with cubics is as far as we have to go. So it's not going to work with quadratics. I've shown you how to do that in a quick way. This is a quick way for quadratics. So I'm going to sketch it. And when I say sketch, I mean sketch. I'm going to draw my x and y axis, and I'm going to roughly plot my points. I'm not even going to put numbers on it. So I have minus 2, 9. That goes about there. and then I have 1/3 minus 100 over 27. If you want to figure that, it's about minus 3.7. So I have 1/3 minus 3.7. So about there, again, I'm not too worried about accuracy here. So that's minus 100 over 27. Now, based on that, can you tell me which one is a maximum point and which one is a minimum point? And hopefully you're saying, oh, yes. So the maximum one is the one that's up higher and the minimum one is the one that's lower. So here is my max point and here is my minimum point. As you get better with this, you're going to realize you just have to look at the Y number. So the Y number, the bigger it is, the higher it is, the smaller it is, the lower it is. The bigger one is maximum, the smaller one is minimum. I find the majority of students will struggle to remember that in the context of the whole course. So sketching, it's a much better idea. But if you're working and you're trying to work as quickly as possible, so I'm talking to those who are aiming for H1s, H2s, every second counts. So you wait 30 seconds drawing it out, try and learn this with the Y value to save you that 30 seconds. It all adds up. So I'm going to go and do that example a second time, but I'm going to use what's called the second derivative test. I'm not a fan of this test and I will only use it if I am made to use it. I think it is long. There is much better ways to do it. Figuring out is it positive or negative quadratic or sketching it like we just did. However, there are times where we can't get away. We need to know this. So when a function slope is is 0 at an x value and the second derivative is less than 0, we know that it's a maximum point. If it's greater than 0, it's a minimum point. So in simple terms, the second derivative greater than 0 gives me the minimum point, and a maximum, the second derivative is less than 0. And that might seem backwards, but can I go back to quadratics here for a second? A positive quadratic, positive, has a minimum point. A negative quadratic has a maximum point. So there is some logic to this, okay? And that's why I kind of did a little bit of the quadratics at the start to really be able to bring this back. So second derivative is greater than 0, it means it's a minimum point. Second derivative less than 0 means it's a maximum point. So let's use that for this example. So we got this far. We've already figured out the points, so I'm not going to bother to do that part again. So it was 1/3 minus 100 over 27. But what we're going to do is we're going to get the second derivative. Sorry, now I've written over things I shouldn't have written over. So I've taken my derivative, f dash of x, and then I have a second derivative. So I have minus 9 was here, and that's 1/3 minus 100 over 27. So my second derivative is 12x plus 10. And I want to check which one is minimum, which one is maximum. So what I do is I do f double dash of minus 2, which gives me 12 times minus 2 plus 10, so minus 24. That gives me minus 14. And because that is negative, so less than 0, therefore, if it's negative, it means it's a max point. We should then find that when we do the same thing here, we should get that that's greater than 0. So it's 12 times 1/3, which is 4 plus 10, which is 14, which is greater than 0, and therefore a minimum point. So I think it's a little bit longer. Remember, in the previous example, I was working through to find the points themselves. In this, I'm only doing what we sketched out. So this is the alternative to sketching. You have to get the second derivative because we hadn't had that up to this point. We then have to do substitution for 2 points. You could argue, couldn't I do it just for 1 point and then the other one would have to be the opposite? Well, if you're going to the trouble of doing this, you might as well do it twice just to make sure that nothing has gone wrong. Because if you got 2 maximum points, you know something's gone wrong. If you get 2 minimum points, you know something has gone wrong. Let's talk about saddle point. I know this is only touched on briefly, but I think it's helpful to have an understanding of this and the type of cubic that has a saddle point. Because often when we see this type of graph, students will say, oh, that's not really a cubic. It is, it's just not our typical cubic. I will show you a graph of this at the end. So it says find the turning point or points of the following function. So now I have ruined this by telling you it's a saddle point, but if you don't know what saddle point is, then it's not ruined. But we may have 2 turning points. We'd expect 2 turning points because it's cubic, but let's see what happens. So dy dx, we're doing turning points. So we're going to differentiate. That gives me 3x squared minus 12x plus 12. Remember that this is slope. To find the turning points, we let that slope equal 0. Well, we know at those turning points, the slope is 0. I can simplify this by dividing across by 3. It's not going to affect anything. X squared minus 4x plus 4 equals 0. So we get x minus 2x minus 2 equals 0, which gives me x equals 2 and x equals 2. And that's interesting. It is interesting because we did get 2 values because it was cubic. However, the 2 values are the same. So is this a minimum or is this then a maximum point? Let's see what happens. Let's find the y value. So y is equal to 2 cubed minus 6 times 2 squared plus 12 times 2 minus 5. This can go into the calculator. That gives us 3. We don't need to do it twice, so that means the point is 2, 3. Now, because we don't have 2 points, this is an example of where we're going to have to use the second derivative. We have no option. So I'm going to do the second derivative here, d squared y dx squared. And that is 6x minus 12. I'm going to sub in 2, so that's 6 times 2 minus 12, which gives us 0. Okay, so we know that if the second derivative is positive, that means it's a positive, it is a minimum turning point. If it is negative, it is a maximum turning point. We haven't discussed what happens if that second derivative is 0. Well, what it's telling us is that this 2, 3 is actually a saddle point. The slope does become a 0, but it doesn't actually have a minimum or maximum. And this is what the graph looks like. And this is a cubic. And you might go, doesn't really look like a cubic. It's a cubic without turning points, so it looks slightly strange. But we have this flattening here. And I suppose we're going to talk about a bit more in the next few slides about this concave up and concave down. And it sits in here. And this saddle point is 2, 3. You can see it there on the graph. There's 3, there's 2. So just to be aware, if we ever get that second derivative equals 0, it's this saddle point. And we're moving beyond saddle point. And we'll talk about what else it means now in a second. But just to be aware, sometimes when we differentiate and let it equal 0 and we get turning points, well, only if turning points exist. Example 4.3. So we're going to investigate some stationary points. This particular example here is quite an unusual example. It has been previously very difficult for students because it's very different to anything else we've seen on the paper. However, if they were to ask this again, I'd hope that students would be able to figure out how to work with it given this example. So the big thing about this question compared to other functions question is the fact that it's defined over a closed interval. So that means that x is only between 0 and 5. So that's the only domain. We often see restrictions in the y, in the codomain, but we rarely see it in the domain itself. So that means we have a very interesting little question here. So we have a function which is defined for the closed interval onto all real numbers. So f of x defined from the domain of a, so between 0 and 5, to all the real numbers where x is given as this. So I'm going to write this out as f of x cubed minus 5x squared. I'm actually going to write it down a little bit lower so we can work with it. So f of x is equal to x cubed minus 5x squared plus 3x plus 5. Now, in order to get the minimum and the maximum points, we would usually do the first derivative, f dash of x, and when we do the first derivative, let that equal 0, because when we do the first derivative, that means slope. And we know that the minimum and the maximum turning points occur when the slope is 0. So we let f dash of x equal to 0. So f dash of x equals 0. So remember, it's where slope equals 0. So we have 3x squared minus 10x plus 3 equals 0 using guide number. But if you prefer, you could actually use your minus b here. No issue at all. 3x squared minus 9x minus 1x plus 3 equals 0. 3x is common, x minus 3, minus 1 is common, x minus 3, and we get 3x minus 1, x minus 3 equals 0, and we get 3x minus 1 equals 0, so x equals a third, and x minus 3 equals 0, so x equals 3. So now that we have that, we can work out f of a third, and we can work out f of 3. So that is 1/3 to the power of 3 minus 5 times a third squared plus 3 times a third plus 5, and that should equal 118 over 27, so not particularly nice at all. And f of 3 is 3 cubed minus 5 times 3 squared plus 3 times 3 plus 5, which will give me minus 4. So the 2 points are a third, 118 over 27, and 3 minus 4. So looking at the y value, so like if you were to just do a little sketch, so you have a third and somewhere up here, and 3 and minus 4. So this must be the maximum turning point, and this must be a minimum turning point. So this is a max turning point, and this is a minimum turning point. However, they didn't specifically ask us for the minimum and maximum turning points. They simply asked us for the minimum and maximum values. There are 2 other possible values that could be minimum and maximum. To understand these, we're going to look at the graph. So we're going to take a look at the graph, and this is what the function looks like. This is drawn by GeoGebra. Now I know in an exam question you're not going to be able to draw this out perfectly. You can't even really do a sketch with any real value in it. However, this is just because we're doing this question as an example for you to get a sense of exactly why we're going to do the next step. So this function that I've drawn here in green basically will go on forever, goes to plus infinity and negative infinity. However, remember that the function itself is actually over a closed interval. So it's only between 2 and 5, or sorry, 0 and 5. So if we band that between 0 and 5, we might get a better sense of what they're asking. So we've worked out a maximum turning point here and a minimum turning point down here. And they asked us the actual minimum value and the maximum value of the graph. You can see by the graph that this point here is most definitely a minimum. The graph doesn't go lower. However, it does go higher than the maximum turning point. It moves somewhere up here. So that means in order to understand if we have actually got the true maximum and true minimum, we need to find two other points, and that point is f of 0, so the start of the interval, and that will be 0 to the power of 3 minus 5, 0 squared, plus 3 times 0 plus 5, which is equal to 5, so that's the point 0, 5. And also the end of the interval, which is f of 5. So that is 5 to the power of 3 minus 5 squared plus 3 times 5 plus 5, and when you do that you get 20. So that's the point 520. So focusing on the y values, you want to find, well, what is the absolute minimum and absolute maximum? This one, because it's a fraction, can be kind of difficult to understand. So although I would always say, you know, leave it as a top-heavy fraction, it's more accurate. This is approximately 4.37-ish. So that way you can get a little bit of comparison going. So we need to figure out what is the maximum and what is the minimum of our turning, well, what is the maximum and the minimum of our actual function. So we can see that the absolute minimum is this point here, but the absolute maximum occurs at this point here. So our two answers are going to be the maximum value of f is 20 and the minimum value of f is minus 4. So it's really important that we, when we have a closed interval, that we deal with the two points that are both at the start and the end of that interval. So we're going to start looking at point of inflection now, and it's important to understand concave up and concave down. So concave upwards is where we have this increase in a slope, and concave down is where we have a decreasing in the slope. So you can see that here. You may, depending on your subjects you study, you may talk about convex, and there is a link to this here, but really we use the word concave up and concave down. So the point of inflection is where the curve changes from concave up to concave down, or concave down to concave up. So just as long as you can recognize that change in curvature, really. So there's three examples here, and the first one is concave down, then we have our point of inflection as it moves concave up. Then we have, in the second example, concave up, and then it turns to concave down. And our third one, it's concave up, and then it moves to concave down. So just to be aware, if we look at the second and third ones, they both are concave up and then concave down, but they look very different because of the way they're positioned. So point of inflection, we're going to use this idea of the concave up and concave down, because when the second derivative is positive, the function is concave up. And when the second derivative is negative, it means it's concave down. And this links back to what we've already done with our minimum and maximum points. Because remember, if the second derivative is positive, then we're talking about minimum points. So it's concave upwards. So that gives us the shape that has a minimum point. When the second derivative is negative, it has a maximum point, and therefore concave downwards actually has what would be the shape of something that has a maximum point. And the point of inflection is dead in the middle, which is exactly where it's going from positive to negative or negative to positive. That means it's at 0. So in simple terms, here is what we have. Concave upwards, d squared y dx squared is greater than 0. Concave downwards, d squared y dx squared is less than 0. And the point of inflection is where that second derivative equals 0. Now, going back to these same diagrams, does that make sense? Concave upwards, you can see it's that kind of shape that would have a minimum point, and that's where the second derivative is greater than 0. It's positive. While concave down has that maximum point, which is why the second derivative is less than 0. It's just to make those connections. Anything to make it easier to remember all this stuff. We've never seen any questions specifically about concave up, concave down, but I think it's really important that you understand all this for you to understand then where point of inflection is coming in. So how do we get the point of inflection? Well, the first thing we do is we calculate the second derivative. We then let that second derivative equal 0 because remember the second derivative is a measure of where is it concave up and where is it concave down. We're saying it's neither, it's in the middle, that's why it equals 0. We solve for our x values and then we use the original function to find y. Very similar to our turning points, but instead of the first derivative, we're using the second derivative. So let's look at an example. Very straightforward. We have a cubic here and we want to find the point of interest or the point of inflection. So y is equal to x cubed minus 3x squared minus 2. So it's missing the x term, but that doesn't bother us at all. It's not going to impact us. So we differentiate this function with respect to x. So we have 3x squared, bring down the power and take 1 away from the power, minus 6x, and 2 is a constant, so it disappears. We're then going to do the second derivative, d squared y dx squared, which gives us 6x minus 6. We let that equal 0. And we get 6x equals 6 and x equals 1. To get the y value, we sub it back into the original, always the original. Because we have an x value, we sub it back in to get the y value. It's a little bit easier when they're written like this. It's a little bit trickier to remember when it's written as f of x. And that gives us minus 4. So my answer is 1 minus 4. You don't need to do any checks. You don't need to sub back in. That's it. Example 6. Verify that the curve y equals x plus 2 over 2x minus 3 has no turning points or points of inflection. Verify that the curve is decreasing for all values of x, where x is an element of the real numbers. So let's start with our y. Now, this is a little bit trickier because we have a fraction, so we're going to have to use the quotient rule. So your quotient rule is on page 25 of your log tables. So 2x minus 3. So my u is the top line, b is the bottom line. Then our formula is, well, dy dx, so the derivative of this is v by du dx minus u dv dx all over v squared. So we'll do a little bit of work over here. So if u is x plus 2, then du dx, so differentiating this with respect to x, gives us 1. If v is 2x minus 3, then dv dx works out as just 2. So this gives us v, which is 2x minus 3, times du dx, which is 1, minus u, which is x plus 2. Make sure you use your brackets to watch your signs. That minus has to be applied to everything. And then dv dx, which is 2, all over v squared. So that's 2x minus 3 squared. Okay. So let's deal with this. We don't even need to clean it up. This is dy dx. the first thing that they asked us to do was verify that it has no turning points. So to get your turning points, we would let dy dx equal 0. Now, if we let this thing equal 0, then we would multiply both sides by the denominator to get rid of the denominator, which would mean 0 by 2x minus 3 squared, which is still 0. So that would leave us multiplying it out as 2x minus 3 minus 2x minus 4 equals 0, which would simplify to minus 7 equals 0, because the negative 2 and plus 2, they cancel, which is incorrect. So we have no value of x that works here, so therefore there is no turning point, because it's not possible for this thing to equal 0. We're going to do the same thing for the second derivative for the point of inflection. So now let's look at this point of inflection. I've just tidied up that dy dx, simplified the top. I've left the bottom as is. The reason I've done that is because it'll make it a little bit easier to differentiate. We won't have to use the quotient rule. If we use our rules of indices, we can bring this bracket above the line and it becomes to the power of minus 2. Now we can use the chain rule, which I think is a little bit easier than the quotient rule, well, quicker than the quotient rule, but you can apply the quotient rule if you prefer. So there's d squared y dx squared. So the chain rule is minus 7 by minus 2. So bring down the power, take 1 away from your power. So it's minus 2, take away 1. So watch out there, minus 3. And then you have to multiply it by the derivative of what's in the bracket, which is 2. So this works out, when we clean it up, as 28 times 2x minus 3 to the power of negative 3. And I'll just try to keep this labelled the whole way down. And then using my rules of indices again, I can bring that bracket to the power of minus 3 back under the line. So it's 28 all over 2x minus 3 cubed. So if I wanted the point of inflection, I would allow this to equal 0. Now we run into the same problem we had before, because if I multiply both sides by the denominator, I'll be getting rid of this. 0 by anything is still 0, so I end up with 28 equals 0, which is not valid. So this fraction cannot equal 0, so therefore there is no point of no point of inflection. Okay, so you're working through it like we're looking for the point of inflection, and then when that fails, like this did, it shows that there is no point of inflection. So the third part of this question asks us to verify that the curve is decreasing for all values of x, element of the real number. So for all real numbers for x, the curve will decrease. So how we prove that something is decreasing, we are going to look at the first derivative. So this first derivative, which is minus 7, 2x minus 3 squared, this will always be a negative number. And the reason I know that is because the top line is negative, because minus 7 is a negative number. And the bottom line, no matter what that x value is, the bracket is squared, which means the whole thing will end up positive. So we get a numerator that's negative, a denominator that's positive, which is effectively a minus divided by a positive, which will end up giving me a negative. So it's going to be less than 0. So that's what's telling us it's decreasing. So since dy dx is always less than 0 for all x element of or, the curve is decreasing. Now, if it was the other way, so if we found that it was always positive, that would mean it's always increasing. Remember, where that's equal to 0, it turns. It's a turning point. So up to the turning point, it could be increasing or decreasing. Then at that turning point, it changes to the other. Given that this has no turning point, it makes complete sense that it is continuously decreasing. It never changes to increasing.